Hey, welcome back to Introduction to Computer Networks. This is Polly again. And guys, we are now in week 5 and episode 9. Okay. So we do have 3 assignments due this week. That includes PA3, the challenging programming assignment. All right. And I noticed that several of you have already started, and some of you actually asked specific questions that many of you might run into as well. So don't forget to go to PA3 to check the Q&As out, just in case that the questions you have already been asked and addressed. All right. And feel free to discuss further on the PA3 channel. And we have 2 more quizzes due this week. Okay, the first one is slightly straightforward, and we might be able to complete that one today. And the second one is extensive. It's going to take you guys some time. It's open-ended, and we're going to work on that tomorrow. So once again, they're due Saturday, 6 p.m., and it's a time that you guys very often forget about because it's in the weekend, and you might be doing something, having fun, and therefore it's easy to forget. So my advice is that perhaps try to complete the assignments by Friday night. That way you can be totally relaxed and go out and have fun for the weekend. Now, there's a heads up. Holly said that this is a gentle heads up, but it's quite a serious head up because you guys know by now, right, how the lectures run and how you participate on the YouTube live channel. And by the way, let me say hi to all of you. So I have not yet say hi to Zhonglun, Bob, Lloyd, Ting-Chi, Vincent, and Junhan. All right, so you know how to participate on the YouTube live chat. You guys also know how to participate in the Discord channel, right? Discord server. And you guys know where to work on the PA assignments and things like that. Something that you haven't really had experience with is just the exams. Okay, so exam 1 is going to be the first one up. This is something that you have probably never experienced before. Okay, so to make it short, in order to prepare you for the exam coming up next week, all right, that's next Wednesday, we're gonna do a 10-minute practice run or test run of your camera, okay, right after the lecture tomorrow. So there's a default office hour that is right after the lecture tomorrow. So Polly would have the camera on. So this is, okay, let me just pretend that I'm starting a new meeting. So Polly would have the session on. This way, you will be able to join and then try out the camera on the laptop or your machine that you're gonna do the exam on. So that you can be sure that the camera is running, audio is running. Okay. And this is the link of the session. Okay, so I should probably do this. Let me copy this over. All right, so Polly is going to be on there. And so you will join and see if your camera is going to be going to work. Okay, so let me close this because for some reason Google changed my camera setting in a way that's a little bit yeah, well, it looks okay anyway. So good. So if you click into the channel exam 1, you will see a lot more. Okay, so Polly has already posted specifics about exam 1. For example, point number 1 is the date and time. It's going to happen 10:20 to 12:10. But you might want to come early to make sure that you're connected and everything is fine. By the way, before the exam starts, Polly would also need to check your student ID. So you need to have your camera on and then you need to show the ID so that I can see the picture on the student ID, picture and the name on the student ID. And so if you blur the background, chances high that the camera will ignore the photo and everything on the ID. So for the ID check, you might need to turn off the blurring, and so that Polly can check the ID smoothly. So second is the exam is going to be on a Google form. Okay, to get a sense, okay, how you need to be prepared to express yourself, okay, on this Google form. You might want to try the old exams out. So there are many of these already, and the Google Forms, a couple example Google Forms are also available. All right. By the way, to access the Google Form, you might need to log into a Google account. You can create one just for the exam purpose. So you definitely need to log into Google in order to use the Google Form. Okay. Number 3, let me see. Yeah, so you will need to join a Google Meet session as well. So you have Google Form here that you'll be typing your solution. There's a Google Meet session ongoing where the camera should be set up. Okay, so this is requiring a working camera, and definitely you need a stable internet connectivity. So tomorrow about noon, when you're doing the testing, you want to be at the place you plan to take the exam to make sure that it's working well. Okay. So this is repeating already. The test run is going to be tomorrow, right after the lecture. So come and try your camera out. Okay. And then Google Meet session is okay. So this session is important for 2 reasons. First is fairness. Okay. Chances high that you guys will be asking questions. So if we all are on this Google Meet session, you will be able to hear other people asking questions, or you will be seeing how other people ask questions, and you will also hear how Polly addressed the questions. Okay, so that way we all can save time. You guys definitely will be able to save time and having more time for the exam. Second is this is also regulated by the university. Okay, this is to make sure that you are there. Okay, and you are very likely the person working on the exam. Okay, and so therefore you want to make sure that the camera is working and it's pointing towards your face. So from shoulder up, essentially throughout the exam, please have the camera set up pointing towards yourself. Shoulder up so that we can see you. Okay, so Polly will also be recording the Google Meet session for the record, just in case the university or the higher party. So by the way, NTU is a public university. We are actually administered by the Ministry of Education. So just in case they need to check on us. Okay. Before the exam starts, you'll be asked to hold your student ID. So that Polly just talked about this. Okay, so the camera ID pointing towards to the camera so Polly can see the name and the face. The scope of the exam depends on the progress of the lecture until next week, the end of Tuesday session. So we'll definitely cover PA 1, 2, 3. Yeah, by the way, Polly has mentioned already in the first week, there'll be questions in the exam that would actually asking you to do programming works, just like what you have done in PA 1 and 3. And in terms of the textbook materials, we'll be covering chapter 1.1 to 1.5. and chapter 1.2 to very likely 2.5. Okay, so we'll be more sure next week, Tuesday. So Polly would update this after Tuesday next week. There are actually more points that are important, but maybe we'll go through these tomorrow where we have a bit more time. Okay, so let me bring you guys back to the lecture and let's take a look at the topics, okay, today. Yesterday, we started introducing the detail of the first application we'll go through in chapter 2, that is web browsing. That HTTP protocol that's supporting web browsing looks simple. Okay, something a little bit tricky that you've learned is there are actually three different modes of maintaining the underlying TCP connection and sending of the requests. Okay, you can send it one by one after getting the response, or you can pipeline them, sending them streamline. One after another, sending the request one after another before receiving the response. Okay, so that's the complication in HTTP. Otherwise, it's very straightforward, client-server based, right? You send a request and you receive a response. And the format of the request and response are all plain text, ASCII based, human readable. So we learned later on there are actually two extra mechanisms, one called cookie, the other called caching. So these are actually to enhance HTTP or enrich HTTP so that HTTP being stateless can potentially be stateful for convenience purpose. And caching is for the purpose of reducing the response time and partly also to reduce the traffic. Okay. So the two kinds of caching we've learned, or the first kind we've already learned last week, it's called local cache. That's where we keep a copy of the web page we often visit. Now, the second one, it's called the web cache. This is the topic we'll start this week. Web cache is not much harder. Okay. Relative to local cache, we keep the web page we visit very often locally on individual client machines. We keep a separate machine, a dedicated separate machine, somewhere between many clients and many servers. Okay, and we call that machine a web cache. Or in the video, we see that they are also called a proxy server, a web proxy server. So in this video, you will see the communication models of HTTP with the proxy server in the middle. This one is 3.5 minutes.
Web caches. The purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. Okay. The main difference is this. In local caching, we keep a copy of the object here. Okay. But now we keep a copy of the object here in the web cache, or also known as the proxy server. Web cache or proxy server. Okay. And in conditional GET, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay, sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client request such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the object somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay. So object in the cache, cache return objects. Otherwise, the cache here, the web cache here, would request from the server a copy of the object. So this request will be like, the proxy server here behaving like a client of the original server. Web cache there, request object from the original server like a client. Okay. And after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, request go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there acts both like a client and a server. As a server, so that it serves the original client, the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So, some of you might see already, right? A web cache like that is actually preferred by the ISPs, okay, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. Okay? So a lot of times ISPs might encourage you to set a web cache, okay, on your browser. Now, let's go through a few examples to detail, okay, why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of example, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving.
All right, so at the sort of later part of the video, you should heard if there's a hit, okay, meaning if the page you're looking for is on the proxy server, then you have the benefit, okay? And as smart as you guys are, you will know that if there's a miss, then it's not that much helpful, all right? But exactly, okay, how much more helpful having the proxy server will be, let's go through an example, okay, a numerical example again, through 3 scenarios, and you will see the benefit eventually using the proxy server, and that depends on the hit rate, okay, of the cache, of the proxy server. So first video is scenario 1. This is to set up the example, okay, and we'll be calculating the response time. Okay, so this video, 3 minutes, 20 seconds.
Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, okay, coming down this way. Right? And that is 1.5 megabits per second. Now, let's see. Round-trip delay from the institutional router to any of the origin servers and back. That's set at to 2 seconds. And the link, access links rate 1.54 megabits per second. And the local area network link rate 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hub, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. But as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right? So close to 1, close to 100% delay, just very long. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here plus round-trip delay here plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay. Now this is very low because utilization is super low. So let's say microseconds, right? So 3 components. Which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here, in terms of delay performance. How do we fix this? Let's look at the second.
Okay, so second scenario is a simple fix. How about expanding the bandwidth of the access link? So that's
good. The example setting is this: servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link.
okay, guys. That I thought. Okay, so let's try it again. So scenario number 2, expanding the access link.
Good. The example setting is this: server.
Okay, I see what's wrong. It seems that I had the link mistaken. So give me a second. Let me update the link, making sure that you get the scenario
Good.
right.
The example setting is this: servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to, in scenario 2, that's try to address.
All right, great. So guys, the reason that I need to play it a couple times is that only when I'm there I can change the link. Okay, so now finally, scenario 2. It's brief, only about 2 minutes.
In scenario 2, that's try to address the issue here, because this is the bottleneck link where the delay came from mostly. And let's blow it up 100 times. How about that? So using a fatter access link there. The result is that the access link utilization is also reduced 100 times. Less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between 2 routers are what? Tens milliseconds and maybe 100 milliseconds at most. So if there's not going to be much queuing delay, yeah, the delay is at this scale. So 2 seconds, milliseconds, microseconds. Which of these 3 components dominates? Obviously, 2. And from scenario 1, we have minutes of delay, to scenario 2, we effectively bring down the total delay. All right, great. Is there any catch? If you think about it, hey, bringing the access link capacity up 100%, that is actually not cheap. So increasing access link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now, in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link.
All right, now scenario number 3. So in this scenario, you will see where we place the proxy server in the example. Okay, and again, towards the later half, when we're calculating the delay, you will see the performance depends just on the hit rate, as I mentioned earlier. So this is scenario number 3, and guys, this one is long, almost 7.5 minutes. Okay, let's see if you guys can hold it to the end.
In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. All right. So we are only slightly local here. So let's see. Good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the two routers. For your information, this could take millions of New Taiwan dollars. But installing a high-end server machines, it only takes this much New Taiwan dollars. So that's about 2 order of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, yeah, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, all right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the clients without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the requests being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the access link. 60% of the scenario one. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client, we have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, saying tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object, the round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content, all right? And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Okay. And you saw a bit already. Next slide. Coming next is going to be the second application in chapter 2. And we'll look at how FTP defines its application layer protocol.
Okay, so now we're not gonna look at the FTP because that one is almost obsolete. And the next one we'll look at is email. Okay, so just like when we're looking at the first application, web browsing, in email, the second application, we'll also start from the communication model, okay, the architecture. So you will see that in email, we have actually 3 components. One is called user agent. What that meant is the clients, the mail readers, okay, or the mail senders, okay. The second component is called the mail server. Now you see from the name, these are the real mail servers helping you sending emails. You know what? The mail servers also help you receive emails, okay. So the protocol, okay, that's running among these mail servers, okay, is called the SMTP. That's the third component. And you will see in this video that there are actually 2 levels of hierarchy because SMTP not only run among the mail servers, it also run from the user agent to the local mail server, okay, or the sending mail server. So there's 2 levels of hierarchies, okay, that the SMTP is running on. Okay, so towards the end of the video, okay, you will see an example. Alice, a user, sending an email all the way to the receiver, Bob. Okay, pay attention to the example, and we're gonna do quiz 12 right after this video. Although that on the topic list, quiz 12 will come later. But today we'll try this. We'll work on a quiz without you guys knowing why yet. Okay, so you guys will be guessing why SMTP or email is designed this way. Okay, so this video, very important, about 5.5 minutes, and right after that, we'll do quiz 12.
2.3, emails. So this application is a little bit unusual. It's supported by not only one application layer protocol, but multiple ones. And we'll talk about it more. Email application. It's got 3 major components. First is the user agent. This is the software running on the machine closer to the users. And mail servers are the software running on more resourceful machines farther away from the users. And among these mail servers, it runs this protocol, SMTP, the Simple Mail Transfer Protocol. These we'll also talk a bit more about that start from the user agent. They're essentially the email readers. They allow us to write email, edit email, read emails. Outlook from Microsoft is one mail reader that's very well known. Thunderbird, I don't know if you know about this one. This is from Mozilla. So the company that produces also Firefox, the very well-known web browser. iPhone comes with a built-in mail reader. Google is also trying to push for a Gmail mail reader. So there are so many of these email readers these days. Now, keep in mind though, the actual emails are all stored on the servers, not on the user agent these days. All right. Now the mail servers. It's got these three major components. The mailbox, which contains all the incoming messages per user. So these are the yellow boxes. When emails come in, they will be sorted out and then put into the email boxes depending on who the receivers are. Second component, the message queue. Those are the green queue over here. So messages that are going out will all be stored here temporarily and waiting for the receiving mail server to open up and then accepting the emails. So SMTP protocol there is to allow the sending server and the receiving server to communicate. Now here in particular, the sending server there is called the client of the SMTP protocol. And the receiving server is, on the other hand, the server of the SMTP protocol. So you see a little bit here, the SMTP protocol is to provide mail receiving service in a sense. So client here, requesting service, server here, allowing emails to come in. If you think about it more, it's got two levels of communications in the email application. So this is one between the end users and the local mail server. Okay, fetching email or pushing email out. But there's another level, which is among the mail servers. All right, so sending mail server is the client of the higher level communication. Receiving mail server is the server of the higher level communication. Then the SMTP protocol. So this is the actual application layer protocol defined to support communication in emails. So let's see, what are the underlying protocols and what is the communication model and what are the messages defined? TCP you see here. Therefore, SMTP is to support reliable email receiving service. It runs on port 25 and the transfer is direct between the sending and the receiving server. The exchange, very simplistic, three phases, handshaking, and then extra transferring of the emails, and then closing. Opening, closing, the extra transferring of the emails in between. The messages are also simplistic. They're just comments coming from the sending server, responses coming from the receiving servers. So comments in ASCII code, just like HTTP, just like FTP. Responses, status words, status phrases, status code, just like HTTP and FTP. They all run in the ASCII code. Now put all three major components together and let me illustrate with a concrete scenario. Alice here is sending an email to Bob over there. All right, so Alice will need to start the user agent first to compose an email. So in the email, it will need to specify the receiver. And then the user agent will send the email to the message queue, okay, in the local mail server. So that is step 2, emails going to the message queue. And then the client side of the SMTP, which is here, this guy is the one sending, and this Bob's mail server will be the one receiving. So this is the client of SMTP. This is the server of the SMTP. So client side of SMTP will open up a TC connection. Once the server is allowing the connection, then the client can begin sending Alice's email. So that email will travel, and the server here of Bob's will check whether the receiver is Bob, and therefore putting the email into Bob's mailbox. Right? So email goes to Bob's mailbox. Lastly, when Bob now joins the internet, invoke his user agent, then the agent already pre-configured to connect to the incoming mail server will then fetch the mail messages, and that's when Bob gets to read the email.
All right, so quiz 12. That Polly explain again, okay, the example, and this time on the whiteboard. All right. Okay, so quiz 12. Alice sending an email to Bob. Okay, so two levels of hierarchy that SMTP runs on. This is the client, this is the server. And in SMTP, the server is always the party receiving emails. Okay, therefore, in the second level of hierarchy, that is higher, this one is receiving email. Therefore, this mail server is the client, and this one is the server. Good. And you know what? SMTP runs up to this point. Yeah, Bob, in order to receive his email, will need to access Bob's local mail server, which is the receiving mail server here in this part. Okay, and we have not yet talked about how Bob access the local mail server to fetch emails. This is through a mail access protocol. Okay, you guys probably have heard about these already, right? When you are setting up your mail reader, it's either POP or IMAP. Okay, so these are popular. But you see, in this case, Bob here is a client using a mail access protocol to read emails from the mail server. And so in in mail access protocol, either POP or IMAP, the server is the mail sender and the client is the user asking for mail. Okay, so it's a little bit tricky. Okay, so for mail access protocol, client access server, server respond to client. And this exchange is similar to HTTP, isn't it? Right? Asking for something and the server responds with something. But in SMTP, hey, the client wishes to send a message, send some significant content. Okay, so SMTP therefore sending data, a huge data right at the beginning. Okay, that's actually to push content out. So this is push-based service, and HTTP and mail access protocol, this is pull-based service. All right. But this is just to elaborate this example. What I'm asking you guys to work on for quiz 12 is this. Why not SMTP all the way to Bob's user agent? Okay, why using another protocol? Why can this machine here just push emails all the way to Bob's client? All right, good. Guys, you have 3 minutes to work on this one. Okay, so this can be a little bit challenging. Okay, brainstorm within yourself or among the teammates. Let's see how you guys come up with. And it's okay if you come up with something crazy, because you guys don't know yet. So feel free to make mistakes. Okay, and chances high that you will make mistakes. But think, why? Right? If we have SMTP for the first part and the second part, what's wrong with running SMTP between the receiver's mail server to Bob's client, Bob's user agent? Okay, let's start counting time. 3 minutes. Guys, love you guys' solutions. Okay, so let's check out some of the solutions. So Yu Zheng here, representing Team 16, says maybe the mail needs to be encrypted by the server beforehand, or the company can offer a cleaner user interface or better user interface for Bob, right? So this is thinking from the point of view that, yeah, we see the current design is that when Bob is the one reading emails, okay, Bob uses the mail access protocol and not using SMTP, because the strengths using a mail access protocols is such that it can provide more cleaner or sort of richer user interface. Okay, so for example, encryption. For example, storing the mails in a specific way, or fetching the mails in a specific way, or forwarding the mails before actually the mails come into the local machine. So this is thinking from the point of view that why, right? Why POP? Why IMAP? Cool, love it. Very different perspective. Ray here says that SMTP would fail to send mail if user agent is not online. Okay, so Ray here, representing Team 23, is thinking, why not SMTP? Isn't it? And the reason is that, okay, so the receiver mail server, if we use SMTP, then the receive mail server will need to push the email out to Bob's user agent, right? So guys, if you are accessing your email from a laptop and you're moving around, right? When you're going from a lecture, from class to class, okay, you're not necessarily connected to the internet. Yeah, indeed, the user agent is not necessarily online. And if the receiver mail just, try to establish connection to a user agent, what's going to happen? Yeah, there's not going to be a receiver, okay, or the other end to establish a connection, isn't it? Yeah, so what would the receiver mail server do then? Would the receiver mail server, periodically try to make sure that the Bob pop up somewhere, or what? Isn't it? So, Ray, yeah, good thinking. Because the mail server, otherwise, if we use SMTP to try to reach Bob's user agent, the receiver's mail server then will need to keep trying and trying and trying. That's going to be a lot of work for the receiver's mail server, right? Very good. Here, Yu Zheng is pushing a mail to you. All right, and let's see Katie. Katie picked it up, right? So mail SMTP is a push service, right? It's actually proactively pushing mails out, okay? So if the recipient is not there, right? If we try to push, the device isn't online, the message could get lost. Yeah, so key point is that, hey, if the receiver mail server here is not implemented correctly or in a right way, in a reliable way, right? The mail server can try to just send it to Bob and forget about it. Wow, then that's really bad, because that message, because Bob is not online, user agent is not connected to the internet, the message would just, disappear somewhere on the internet, right? Good thinking, good thinking. Yeah, this might not be really what happened on the internet if you just push it out without caring much, because the underlying protocol is TCP. But good thinking, yeah. So I ask you guys to guess, and this is very close to the case. Okay. Let's see. 正年, Bob's user may not be always online. The connectivity would. Okay, good. 正年 here pointed out that, hey, in the video you heard that the underlying protocol is TCP. So before the email can be pushed, right? between the receiver mail server and Bob's user agent, we need to establish a connection. But wait, how do you establish a TCP connection, right? You need to know Bob user agent's IP address and the port number first, isn't it? Recall. Establishing a socket, right? You specify its TCP, you specify the IP address and port number. But if Bob is not online at all, there's not going to be an IP address or a port number, okay, for the receiver mail server to connect to. Exactly. Okay, so this is going to the detail and getting closer and closer. Okay, guys? Wonderful. Okay. And you know what, guys? This is all the time we have for today. So we're going to go through, so Polly is going to go through all you guys' solution and comment in case I find anything interesting. But let's close the lecture today. And tomorrow we'll continue to talk about the rest of the email application protocols. We have not yet talked about the messages we actually exchange, the format of the messages. We have not yet formally introduced the mail access protocols. Okay, so tomorrow, first thing, you will hear about these. And then we'll move on to talk about the third application called DNS. Okay, so let me not talk too much about DNS. You will definitely hear all the details. Okay, we want to communicate about DNS. So come tomorrow, 10:20 sharp, and I'll see you tomorrow. All right, bye. All right, guys, go. Just come tomorrow. Bye. Bye. Okay, bye. Are not servers. Oh, very good point. They are not servers. They don't have a fixed IP address. It's in fact impossible for the receiver mail server to find, right? To establish a connection to the user agent. Very good. Always online. That's one obvious reason. Yes. Okay, very good. Always online. Always online. Very good. Receiving agent. Exactly. Okay, very well elaborated. Okay. Annabelle, good job. In here, Alice mail server may not have the same protocol. Oh, interesting. Okay, Ethan is actually proposing a solution to enable SMTP to go all the way. That's wonderful. Have have storage capability. It's not online. That send will be lost. Yeah, therefore, SMTP, the sending side, okay, will need to be able to wait until at least establishing a connection and sending. Yeah. It's temporary storage, I would say. Might be offline when the mail is sent. Ah, okay. Yeah, so this is a very common reason. Mm-hmm. Very good. The mail servers will need to hold these emails. Okay, now you know that it's actually pulled from the receiving user's end. Okay, good. Very good. Yeah, may not successfully connect. Okay, good. Oh. Okay. Yeah. So as a push protocol, the receiver needs to be online all the time. Okay, much like a server. And ready for a connection, having a IP addresses that is known to the sender. And so instead we use the access protocol because the user agent at the receiver side is no way, right? It's kept online, having a global IP address. Okay, so this explains why. Very good. Well elaborated. Let's see, Jordan. Oh, okay. Very interesting. Love it. Okay, it's better actually keep the client's Bob's user agent offline, right? Instead of keeping it all the time. Love it. All right. Okay, good. Okay, I think that's all.